What if the darkest object in the universe was born inside Albert Einstein's mind before anyone ever saw it? A place where gravity becomes so powerful that light cannot escape. A place where time slows down, space bends inward, and the laws of physics reach their breaking point. Today we call it a black hole. But when Einstein created general relativity, he was not trying to discover monsters in space. He was trying to answer one simple question: what is gravity really? For more than 250 years, Newton said gravity was a force. The sun pulls the earth pulls the moon. Every object attracts every other object. It worked. But Einstein looked deeper. He asked, what if gravity is not a force pulling through space? What if gravity is space itself bending? That idea changed everything. Suddenly, planets were not being dragged around the sun. They were moving through curved space-time. Light was not traveling in a straight line anymore. It could bend around stars. Time was not the same everywhere. Near strong gravity, time could slow down. And hidden inside this beautiful theory was something terrifying. Einstein's equations suggested that a dying star could collapse so completely that it would create a boundary of no return. Cross it, and even light cannot come back. Einstein did not want to believe it. He thought nature would never allow such a thing. But the universe had already made its decision, because decades later, scientists would discover neutron stars, pulsars, gravitational collapse, and finally black holes. The strangest part? Einstein's own theory predicted them before Einstein himself accepted them. So this is not just the story of black holes. This is the story of how Einstein defeated Newton, then watched his own theory escape his control and reveal a universe far darker, deeper, and more mysterious than even he imagined. To understand why black holes disturbed Einstein so deeply, we first have to understand what he did to gravity. Before Einstein, gravity belonged to Newton. Newton's idea was powerful and simple. Every object with mass pulls on every other object. The Earth pulls the apple. The sun pulls the Earth. The Earth pulls the moon. And for more than 2 centuries, this picture worked beautifully. It predicted planetary motion. It explained falling objects. It helped astronomers calculate eclipses and orbits. Newton's gravity was one of the greatest achievements in human history. But Einstein noticed something strange. Newton explained what gravity does. But he did not fully explain what gravity is. How does the sun pull the Earth across empty space? How does the Earth know where the sun is? Is gravity an invisible force traveling instantly through the universe? Einstein was not satisfied with that. He wanted the hidden mechanism, and the first clue came from something extremely ordinary: falling. Imagine you are inside an elevator, and suddenly the cable breaks. For a moment, you and everything around you begin to fall together. Your feet no longer press against the floor. A coin floats beside you. A pencil floats beside you. You feel weightless, but gravity has not disappeared. The Earth is still pulling you. The elevator is still falling. Your body is still accelerating downward. Yet from inside the elevator, it feels as if gravity has vanished. This simple thought shocked Einstein, because it showed him that gravity was not like other forces. If you are in free fall, gravity can disappear from your experience. You do not feel it. You float inside it. That idea became the seed of general relativity. Einstein realized that falling objects are not being pulled in the ordinary way we imagine. They are following the natural path through curved space-time. This was the revolution. Space is not empty nothingness. Time is not a universal clock separate from space. Space and time are joined together into one fabric, space-time, and matter changes the shape of that fabric. A planet curves space-time a little. A star curves it more. A dead massive star can curve it violently. So when Earth orbits the sun, it is not because the sun is pulling Earth with an invisible rope. Earth is moving through curved space-time, following the path that the sun's mass creates. This is why general relativity sounds strange at first. It does not describe gravity as a force. It describes gravity as geometry. The shape of space-time becomes the gravitational field. And once Einstein saw gravity this way, the universe changed. A straight line was no longer always straight. Time no longer passed the same everywhere. Light itself could bend, but having a beautiful idea was not enough. Einstein needed mathematics strong enough to carry it, and this was not easy. Curved space-time could not be described with simple school geometry. Einstein needed advanced geometry, tensors, and equations that could connect matter, motion, curvature, and time. For years, he struggled. He had the physical vision, but the mathematics fought back. This is where his old friend Marcel Grossmann became important. Grossmann understood the geometry Einstein needed. He helped Einstein find the mathematical language that could describe a universe where space and time bend. Together, they pushed toward a new theory of gravity, but Einstein still needed proof. A theory can sound beautiful and still be wrong. So he looked for a place where Newton's gravity had failed. He found Mercury. Mercury is the closest planet to the Sun, so it lives deep inside the Sun's gravitational influence. Its orbit slowly shifts over time. The closest point of Mercury's orbit, called its perihelion, moves slightly with each orbit. Most of this motion could be explained by Newton, but not all of it. There was a small difference that refused to disappear. For years, astronomers knew something was missing. Some even imagined another hidden planet near the Sun, pulling Mercury slightly out of place. But Einstein did not need a hidden planet. He used curved space-time. Near the Sun, space-time is not flat. It is curved strongly enough to change Mercury's path in a way Newton's theory could not fully capture. When Einstein calculated Mercury's orbit using general relativity, the missing number appeared. The puzzle clicked into place. For Einstein, this was a powerful sign. His theory was not just beautiful. It was seeing deeper than Newton. But Mercury was only the beginning. General relativity made an even stranger prediction. Gravity affects time. The stronger gravity is, the slower time passes. This sounds impossible if you think of time as one universal river flowing equally everywhere. But Einstein showed that time is not universal. A clock near a massive object ticks more slowly than a clock far away from it. On Earth, this effect is tiny, but it is real. Modern atomic clocks can measure it. Even a small difference in height can create a tiny difference in the flow of time. This means the universe does not have one master clock. There is no single now, shared equally by every planet, star, and galaxy. Each place has its own time, shaped by gravity and motion. Near weak gravity, time moves one way. Near strong gravity, time slows. Near a black hole, time becomes almost unrecognizable. But before black holes entered the story, Einstein needed one dramatic public test. If gravity is curved space-time, then light should bend when it passes near a massive object. This was shocking. Light has no ordinary mass. So under Newton's older picture, people did not expect gravity to treat light in the same deep way. But Einstein's theory said light follows the geometry of space-time. If space-time curves near the Sun, then starlight passing close to the Sun should also curve. The problem was simple. How do you see stars next to the Sun? During the day, sunlight hides them. The only chance was a solar eclipse. When the moon blocks the Sun, stars near the Sun become visible. Scientists could photograph their positions and see whether their light had bent. In 1919, Arthur Eddington helped lead eclipse observations to test Einstein's prediction. The result changed history. The starlight appeared shifted exactly in the direction Einstein's theory predicted. Light had bent around the Sun. Newton's universe had been shaken. Einstein became world famous almost overnight. Newspapers called him a genius. People who barely understood relativity still knew his name. The world saw him as the man who had changed space and time. But inside this triumph, something darker was waiting. because the same equations that explained Mercury, bending light, and slowing time also contained a disturbing possibility. In 1916, Carl Schwarzschild solved Einstein's equations for a simple case: space-time around a perfectly round, massive object. It was a brilliant achievement. Einstein's equations were difficult. They did not behave like ordinary formulas. Yet Schwarzschild found an exact solution. But hidden in that solution was a strange boundary. At a certain radius, the mathematics became extreme. Time behaved strangely. Space behaved strangely. The equations seemed to point toward a region where normal physics could no longer speak clearly. This became known as the Schwarzschild radius. At first, it looked like a mathematical problem, a strange feature inside an equation. But its meaning was terrifying. If enough mass was squeezed inside that radius, gravity would become so strong that escape would be impossible, not for a rocket, not for matter, not even for light. This was the seed of the black hole. Einstein did not like it. To him, this kind of collapse seemed too extreme to exist in nature. A star collapsing into a region where space and time lose their ordinary meaning. A boundary where light can enter but never return. A center where the equations point toward infinity. It felt less like physics and more like a warning that the theory had reached its limit. Einstein believed nature would avoid such a disaster. He thought real stars would never collapse in this impossible way. And for a time, many physicists agreed. Black holes seemed like mathematical ghosts, strange objects that could appear on paper, but not in the actual sky. After all, the sun would have to be crushed into only a few kilometers to become a black hole. Earth would have to be squeezed down to the size of a small object. This sounded absurd. The universe was strange, yes, but surely not that strange. Yet general relativity refused to stay gentle. It kept pointing toward stronger gravity, deeper curvature, and more extreme endings for massive stars. Einstein had opened a door, and behind that door was a universe even he was not ready to accept. Because if stars could die, if massive stars could collapse, if gravity could overpower every force trying to hold matter apart, then the black hole was not just mathematics, it was destiny. And the next generation of scientists would have to face the possibility that Einstein's greatest theory had predicted the darkest objects in existence. For many years, black holes lived in an uncomfortable place between mathematics and reality. Einstein's equations allowed them, but many scientists still ask the same question. Can nature really make something like this? A black hole was not just a heavy star. It was not just a dark planet. It was a region where space-time curved so deeply that every path led inward. To escape Earth, you need enough speed. To escape the sun, you need even more speed. But inside a black hole, the required escape speed becomes greater than the speed of light. And because nothing can outrun light, nothing can escape. This is why the boundary of a black hole is called the event horizon. It is not a surface you can touch. It is not a wall made of matter. It is a point of no return in space-time. Outside the event horizon, light can still move away. Inside the event horizon, even light's future points inward. This idea was so disturbing that Einstein resisted it. He believed real stars would not collapse into such impossible objects. But after Einstein, the theory kept moving. In the 1960s, Roger Penrose showed that black holes were not just a mathematical trick caused by perfect symmetry. Under the right conditions, if a massive star collapses far enough, general relativity naturally leads to a trapped region, a place where light is forced inward, a place where collapse cannot be stopped by ordinary physics. This was a major turning point. Black holes were no longer strange shadows hiding inside equations. They became serious predictions of Einstein's own theory. Then the universe gave scientists another clue. In 1967, Jocelyn Bell Burnell detected strange radio signals from space. Pulse, pulse, pulse. The signal repeated with astonishing regularity. At first, it looked impossible. What kind of object in space could blink so fast and so precisely? The answer was a pulsar, a spinning neutron star, a dead star so dense that the mass of the sun could be packed into a sphere only about the size of a city. This discovery changed the imagination of physics. If neutron stars existed, then dead stars could become far more extreme than anyone once believed. And if a neutron star had too much mass, even that final structure could fail. Gravity would win completely. The star would collapse past the event horizon. A black hole would be born. Einstein had doubted this ending. But the universe was beginning to show that his equations knew more than he did. That is one of the most beautiful and frightening things about science. Sometimes a theory becomes bigger than the person who created it. Einstein opened the door to curved spacetime. But behind that door, the universe revealed objects so strange that even Einstein hesitated to accept them. And black holes were only the beginning. Because once scientists accepted that black holes might exist, a deeper question appeared. How do you prove something is there if no light can come from it? You cannot see a black hole directly the way you see a star. So scientists looked for its fingerprints. They watched stars orbit invisible objects. They studied gas spinning violently around dark centers. They detected X-rays from superheated matter falling toward extreme gravity. They measured stars moving around the center of our galaxy as if controlled by something massive, compact, and unseen. The evidence kept growing. Then, in the modern era, humanity finally captured the shadow of a black hole. Not a normal photograph, not a simple camera image. It was built from radio telescopes across Earth, working together like one giant planet-sized telescope. The image showed a glowing ring around a dark center. That dark center was not emptiness. It was the shadow of the event horizon. For the first time, the world saw the shape of something Einstein's theory had predicted more than a century earlier, a darkness made visible by the light it trapped. But even after seeing black holes, the mystery did not end. It became deeper, because according to general relativity, inside a black hole, the collapse may continue toward a singularity, a point where density becomes infinite, a place where space-time curvature becomes extreme, a place where Einstein's theory seems to reach its own limit. And this is where physics becomes uncomfortable. General relativity works beautifully for planets, stars, galaxies, bending light, gravitational waves, and black holes. But at the center of a black hole, it points toward a place where its own language breaks down. It tells us something is missing. Einstein gave us the greatest theory of gravity ever created. But even his theory may not be the final answer, because deep inside a black hole, gravity becomes extremely strong and matter becomes extremely compressed. At that scale, quantum physics should matter too. And this is the great problem. General relativity explains gravity and space-time. Quantum mechanics explains particles and the microscopic world. Both are incredibly successful. But when scientists try to combine them inside a black hole, the theories do not fit easily. It is as if nature is speaking two languages at once. One language for the huge, one language for the tiny. And black holes force both languages into the same sentence. That is why black holes are not just objects in space. They are testing grounds for the future of physics. They ask questions we still cannot fully answer. What is time inside a black hole? What happens to matter after it crosses the horizon? Does information disappear forever? Can space-time itself break? Or does a deeper theory replace the singularity with something else? Some scientists believe quantum gravity may remove the singularity. Instead of collapsing into infinite density, matter may reach a smallest possible scale. Some theories suggest a bounce. Some suggest information is stored on the event horizon. Some suggest space-time itself emerges from deeper quantum information. No one has the final answer yet, but every serious attempt points to the same truth. Black holes are not the end of science. They are the place where the next science may begin. And this brings us back to time. Einstein showed that time is not universal. Gravity slows it, motion changes it. Near a black hole, this becomes extreme. If you watch someone fall toward a black hole from far away, they would appear to slow down near the event horizon. Their light would stretch, redden, and fade. To your eyes, they would seem frozen at the edge, but for the person falling in, time would feel normal. They would cross the horizon without seeing a physical wall. Two observers, two different experiences, one reality. This is what Einstein forced us to accept. Reality is not always what it looks like from one point of view. Space and time are not fixed backgrounds. They are active. They bend, they stretch, they respond to matter and energy. And near a black hole, they behave in ways that challenge every instinct we have. That is why black holes feel terrifying. Not only because they trap light, but because they trap our common sense. They show us that the universe is not built for human comfort. A star can die, gravity can win, time can slow, space can curve into a prison, and the laws that seem familiar on Earth can become strange at the edge of the cosmos. Yet this is also what makes black holes beautiful. They are not chaos. They are not magic. They are consequences. Consequences of Einstein's equations. Consequences of gravity taken seriously. Consequences of a universe where space and time are real physical things. Einstein once replaced Newton's invisible force with curved space-time. That single idea explained Mercury's orbit. It explained bending starlight. It explained gravitational time dilation. It predicted gravitational waves. And it opened the path to black holes. Even when Einstein doubted them, his theory kept pointing toward them. And in the end, the universe chose the theory over Einstein's doubt. That may be the most powerful lesson of this story. A great scientist is not great because he is always right. A great scientist is great because he gives humanity a way to discover where he is wrong. Einstein gave us equations so deep that they revealed truths he himself struggled to accept. Black holes were one of those truths. And today, more than 100 years later, general relativity is still alive. It still guides astronomers. It still helps us understand the expansion of the universe. It still describes the motion of planets, the bending of light, the ticking of clocks, and the collision of black holes. But it also points beyond itself. At the center of a black hole, Einstein's theory seems to say, here is the edge, here is the mystery, here is where a new idea must begin. Maybe the next revolution will unite quantum mechanics with gravity. Maybe it will change our understanding of time. Maybe it will show that space-time is not fundamental. Maybe it will reveal that black holes are not endings, but doors to a deeper structure of reality. We do not know yet. And that is exactly why black holes matter. They are not just cosmic objects. They are questions made of gravity. They ask what space is. They ask what time is. They ask whether information can be destroyed. They ask whether the universe hides new laws behind its darkest boundaries. Einstein once showed that the universe was stranger than Newton imagined. Black holes now show that the universe may be stranger than Einstein imagined. And somewhere inside that darkness, physics is still waiting for its next great answer. So when you look at a black hole, do not think of it only as a place where light disappears. Think of it as the final test of Einstein's universe, a place where gravity becomes geometry, where time becomes fragile, where space becomes a trap, where a dying star becomes a question mark written across the cosmos, and where the greatest theory of the 20th century points toward the greatest mystery of the future. If this story changed the way you see black holes, subscribe to the channel, because here we explore the universe through Einstein's deepest ideas. And before you go, comment below. What feels more terrifying to you, that black holes exist, or that Einstein's own equations predicted them before anyone could see them?